So here's a theorem for you. Maybe you might want to press pause and have a quick read for yourself. So what it's saying is that if you have a sequence an over bn, so our first term will be a1 divided by b1, our second term will be a2 divided by b2, and so on. So it's actually one thing, the sequence is actually one thing divided by another thing. Well, if this thing here is satisfied, so what it's saying is that if the limit of our sequence here converges to some sort of limit c here. If this c here is bigger than 0, if this thing is satisfied, then the series, if this series diverge, then this series here will also diverge. If this series here converge, then this series here will also converge. So remember, this thing has to be satisfied. If this thing here is satisfied, if it converges to some sort of limit c, and c is above 0, then these two will act in unison with each other. Meaning, if this thing diverge, then this thing here will diverge. If this thing here converge, then this series here will also converge, and so on. So we've done this. We will come back to this later on. But now let's look at number 2. So it's saying if this here, if the limit is equal to 0, so if the limit of, so now we are not looking at this now. We are looking at a case where the limit equals 0. So it's heading towards 0. So it's heading towards 0. We are looking at this scenario now. If it's heading towards 0, and the bottom series converge, then the series at the top must also converge. So for example, what it's saying is that if this thing here converge, if this series here converge, then the top one must also converge, because you can't have a case where let's say this thing here converges to 7, and then you can't have a case where this will just diverge. This will get bigger and bigger and bigger. You can't have a case where this, you see, then the whole thing here will diverge. But then you've got a condition placed on you that this thing here must converge to 0. So let's start again. If this thing here heads towards 0, if the limit is 0, and this thing, if this thing here converge, so let's say it converges to 7, then the top one will have no choice but also to converge. So maybe it converges to, I don't know, 0.00007 say, or 3 say. But the numerator cannot diverge. It must converge. It cannot diverge, because for it to diverge, then it's saying the numerator will just get bigger and bigger and bigger and bigger, meaning that the limit won't be 0. But the condition right from the start was that the limit must equal 0. So basically, if the limit equals 0, the limit of this sequence equals 0, and this thing here converges, then the numerator must also converge. Okay. So now let's look at number 3. So this condition here, if this is satisfied, meaning the limit goes to infinity, then and the limit, so the series at the bottom diverge, then the numerator must also diverge. So for example, if you have something that keeps on getting bigger and bigger at the bottom, then the numerator cannot converge. Let's say that the numerator cannot converge to, let's say, 5. Otherwise the limits here will head towards 0. The limits here will head towards 0. But we said the condition right from the start was that it's heading towards infinity. Why there? If it heads towards infinity and this thing here diverge, so this thing here gets bigger and bigger and bigger and bigger and bigger, the numerator cannot converge. So therefore it must diverge. It must diverge. It cannot converge. It cannot converge, because if it converges to, say, let's say 300, then you can see that this thing here is heading towards 0, but it must head towards infinity. So in the next video, we're going to try and prove this. Okay, these two are quite straightforward, but let's try and prove the first one in the next video. Okay.